MOSFETs are the building blocks of modern electronics, but their theoretical subthreshold swing limit of 60 mV leaves a lot of room for improvement in this space. Tunneling field effect transistors, or T-FET, have quite a significant improvement on this subthreshold swing, and adding that to the improvements in low off-state current, they can pave the way to the future when it comes to semiconductor technology. But what exactly is a T-FET, and how does it bring forth these seemingly massive improvements? Let's see. T-FETs generate current through the use of quantum tunneling effect. Quantum tunneling is the phenomenon where an electron can pass through a potential barrier even though they're at a lower energy state. Now, if we see the construction of a T-FET and compare that to the traditional MOSFET, it will all make sense. As we can see, the source and drain of the regular MOSFETs are made from the same N-type material, while the channel is P-type. In the case of T-FET, the drain remains N-type, but the source becomes P-type and the channel becomes fully intrinsic. The difference in construction makes it so that there will be a major difference in the energy band diagram of each device. Here we can see the energy band diagram for MOSFETs, and here we can see the same for T-FETs. Now if we turn the T-FET into the on state or apply voltage to the gate of the FET, the band diagram will change into something like this. And we can see there's a small barrier through which the electrons can effectively travel due to the quantum tunneling phenomenon, and the current flow occurs. And since this tunneling is only possible in the on state, T-FETs have very little leakage current. Another reason why T-FETs are such a big deal is their low subthreshold swing. Subthreshold swing is a measure of how much of an increase in voltage is needed for enhanced or increased current flow. So obviously the smaller we can get this value, the better our devices will be. In this rough graph, we can see the subthreshold swing for an ideal switch, for a MOSFET, and for a T-FET. The lower leakage current of T-FET compared to MOSFETs can also be observed in this area of the curve. T-FETs are currently seen as the next generation of MOSFET technology, and while uses of T-FET in consumer electronics are still at an early stage, moving forward it is a strong replacement for everything the regular MOSFETs can do. Companies like Toshiba and Samsung are committed to this new technology for FET devices, and consumers as well as industrial electronics from system on a chip to DRAMs can be made more efficient as well as more powerful with the use of T-FETs. Some other potential devices that can be made from T-FETs are point-of-care diagnostic biosensors, neural network-based associative memory, and ultra-low input power conversion circuits. With this technology, we can really push the limits of the famous Moore's law. Please check the description of the video for any and all references and other relevant links, and thank you.